mixture that you got in the lab was intentional. I took 3 things, I intentionally mixed them together and gave it to you to see if you could sort it out. Not all mixtures are intentional. So we get into this idea of purity and chemicals, and chemists do, frankly, laugh when people talk about, there are chemicals in the water. Well, water's a chemical. The air you're breathing is a chemical. It's a chemical mixture. So we can have a chemical that we produce for some reason that isn't quite pure. And I've got my, my favorite little impure chemical substance right here. I think I've already introduced you to my friend. What is my friend? It's sodium chloride. It's sodium chloride with a lot of other stuff in it. So if you notice how sort of dark and dingy and dirty the bottom of that chunk of sodium chloride is, and I put away the other sodium chloride, but that's not a very pure sample. Now that was mined straight from the earth. That salt deposit, there's a vein of salt, I don't know, 20 or 30 feet thick underneath Lake Erie. It's an ancient ocean. What else was in that ocean? Oh, invertebrate poop and dead fish and, fish poop and shark poop and, everything else dead and decomposed. And that all sinks to the bottom of the ocean. And if you look at the salt deposit, you'll see these bands of basically poop. Okay, it's crud, it's other stuff. But these bands of impurities. And they mine that stuff there at Geneva. They don't really clean it up. You know where that stuff goes for the most part? You drive on it in the winter. It doesn't matter if there's a bunch of fish poop on the road whatsoever. It does not have to be very pure. Now, if you are selling salt for consumption, people are going to eat it. It has to be a little bit purer. So you typically take the fish poop out, and I have put away my container of, oh, here's one. Container of sodium chloride. Here we go. So this is actually lab grade sodium chloride. This is kind of what they sell what's called reagent grade. It's a primary grade reagent, something that is prepared and purified to be used in a chemical lab. You may have heard a reference to something that being pharmaceutical grade. That's a primary grade reagent. So throwing it on roads, making big batches of industrial who knows what with it, doesn't have to be all that pure. Which do you think would be purer? Chemicals prepared for human consumption or chemicals prepared for like a pharmaceutical lab, primary grade reagents? Pharmaceuticals. One of the issues, what can happen with a reagent that is not as pure as it needs to be if you're making drugs? If you're making drugs, you are making chemicals that are going to interact with biological systems. Whether you're making insulin, whether you're making albuterol, whether you're making an antibiotic. So you're making a chemical that is intentionally going to be placed into a biological system, that's a person, and intentionally interact with their biochemistry. If there are chemicals in there that you don't expect, they can react in ways that are unexpected. So an impure batch of a pharmaceutical, of course, it can do everything from have minor side effects to kill someone. So primary grade reagents and pharmaceutical grade reagents are the purest class. You eat something that has some extra other molecules in it, your body can sort it out pretty well. Because it's going through the digestive system, it's not interacting in the same way, it's not as biochemically active as a drug would be. So they're rated based on that level of purity. Everything that we use in here is primary grade reagents, though I will admit that occasionally, for some labs, we do sneak in what is a non-primary grade reagent. Every now and then over the years when I've run out of reagent grade sodium chloride, I go buy a thing of cheap non-iodized salt at Shop and Save, and we call it a day, and you never know the difference. It's still pretty darn pure. But it's not a primary grade reagent. It's not a pharmaceutical grade or reagent grade chemical. Okay, so looking at your what do you knows, you guys had a pretty good sense of what elements are. If you cannot find it on the periodic table, it's not an element. Period. And the periodic table, of course, is, whoops, well, shoot, custom, this thing. There's the periodic table. This is a very basic one. It's called the Van Brainer periodic table. We'll use it throughout the year. If it's not on here, it's not an element. If it is on here, it is an element. Never mind the fact that the ancients had these kind of wacky ideas, and we maintain some semblance of this, that earth, air, fire, and water were the elements. The fifth element being spirit. Those are not. Those are other substances. Water is a compound made of two elements, hydrogen and oxygen. Earth is a mixture of a whole lot of substances. Actually, do you know what the most abundant element in the Earth's crust is? You had to guess? In the crust. In the atmosphere, yes. In the crust, no. It's oxygen. You don't think of oxygen as rocking, do you? SiO2 is silicon dioxide. It's a primary component of a lot of minerals. So we have a lot of oxygen in the Earth's crust. Okay, fire is actually, what is fire? It's orange and red, and it gives off heat, and it's nice to sit around on a fall evening. What is it? Not fire. Burning is. Combustion is. Fire itself is not a reaction. It's a substance. It's an actual substance. What is it? It's a state of matter. What state of matter is it? Close. You're getting warmer. What's more energetic than gas? Plasma. Plasma is a superheated gas that glows and gives off light. Guess what fire is? It's a superheated gas that glows and gives off light. It's plasma. So it is plasma of the various products of combustion. Okay. If it's not on here, it's not an element. What's neat about these things, all of them, is we can isolate it down to a single atom of any of these: aluminum, phosphorus, copper, calcium, you name it. And they have their characteristic qualities. And we're going to examine those as we go in more depth. But if it's not on here, it's not an element. If it is on here, it is an element. For some reason, this one is darker. I do not know why. A few of you said in your what do you know that you were aware of groups and periods. The best mnemonic that has ever been done for this one is one that came from a sophomore about 10 years ago. Gravity goes up and goes down. Gravity. With age comes. So that was the best mnemonic that I've ever heard, because I used to actually struggle with which are the groups, which are the periods. Groups go down, gravity pulls things down, G for gravity. So the groups are the columns, they're up and down. Groups have similar chemical properties. We can predict something's chemical properties based on its group. The rows are called periods, and they have nothing to do with chemical properties. You cannot predict anything about chemical properties based on the row something is in. And you probably had a sort of brief intro to that in physical science. So that's a group. You can predict properties. That is a period. Completely unpredictable in terms of chemical properties. Questions on that? I think most of you, based on your what do you know, Most of you kind of already had that sense. You may have not remembered which was a group, which was a period, but I think you had some sense of it. And I asked you this question in your what do you know? Metals are good conductors. They're good conductors of both heat and electric. You've all probably gotten shocked by a doorknob when it either took extra electrons off your skin or deposited extra electrons on your skin. Metals tend to be solids at room temperature. There's one exception. What is it? You don't get to play with it anymore. Mercury. When I was a kid, my friend Kelly's brother John, who was an evil, mad genius kind of kid, had a baby food jar full of mercury that he had collected by breaking thermometers over many, many years. Oh my gosh, we had so much fun with that stuff. You could roll it around in your hand. We're all just fine. Most of them are solid at room temperature. The notable exception is mercury. They can be hammered into thin sheets. That characteristic is called malleability. Who here has ever interacted with a thin sheet of metal? What did you interact with, Michael? Huh? Tin, okay. The most common one is this one. This is a thin sheet of aluminum atoms, nothing but it. When they call it aluminum foil, they're not kidding. It really is aluminum. And a foil is what we call the thinnest possible sheet of any metal. You can get gold foil, silver foil, copper foil, a lot of art. There are a lot of art applications for some of the metallic foils. Sometimes people will do what's called gold leafing, and they actually press very thin foil sheets of gold onto a surface. The Imperial Palace in Russia, I think, is an entire room that's covered in gold leaf just because they can. They're ductile. That's the ability to be pulled into thin wires. Our entire world right now is running on thin wires of one particular metal. What is it? Copper. We're running with all these electrons flowing through these little tiny thin wires. And you heat this stuff up and you can pull it into amazingly thin wires, things that are, you know, a couple atoms across, if you're really careful. Copper's used in wiring. We use metals medically in a few ways. Lithium is something that's used to treat chemical imbalances in the brain that cause bipolar disorder. We're living with a whole lot of metals. However, metals are not only the ones you think of. So let's look at the periodic table again. All of these things. Oh, and I always forget exactly where the line is. Oops. Yeah. Something like that. And I'd have to look at your book for an exact line. But basically all of those things, well, I think these two also, are considered metals. Okay? So things like potassium, it's a metal. Sodium is a metal. You don't often get to see solid sodium. I have a periodic table with pictures of all the elements, and it got kind of wrecked, so I'm working on getting another one. But solid sodium is this sort of, it looks like Play-Doh, but sort of shiny. Metals tend to also be lustrous, they call it. They reflect light. They have a little bit of a shine. And polished metals were used as mirrors. You can still get unbreakable camping mirrors that are just polished, usually polished stainless. So and that's actually related to their ability to conduct heat and electricity, because they're reflecting light, and it's similar to, it has to do with the arrangement of their atoms. Okay, the next kind of element that we're going to talk about, well, you heard about the metals, now it's time to talk about the non-metals. So if you have a sibling who is your polar opposite, who is everything you are not, you are friendly and personable, they are crabby and antisocial. You are brilliant, they are dull. None of you have a dull, antisocial, crabby sibling, I'm sure of it. Metals and non-metals are those kind of polar opposites. Everything that metals are, non-metals are not. So my husband and his brother, I have often heard, my husband, before he met me, used to be very neat and very orderly, and his brother is more like me, and they shared a room. you can imagine the sorts of fun and delight this led to. If you have a sibling, if you are neat and organized and everything's color-coded and lined up and put away and well-organized, and your sibling walks through the room and 5 seconds later it looks like a tornado tore through, that's the metals and the non-metals. They are polar opposites. Metals are good conductors. Non-metals are lousy conductors. Metals are solids at room temperature with that one notable exception. Non-metals tend to be gases. Metals can be pulled, stretched, hammered. Non-metals shatter if you do that kind of stuff to them. They're brittle. There aren't a whole lot of non-metals. They're sort of a minority. There are fewer of them. And the big three that we look at in terms of atmosphere are carbon, oxygen, nitrogen, in the form of carbon dioxide, elemental oxygen, O2, elemental nitrogen, N2, and then we've got other carbon compounds like methane that end up in the atmosphere. Hydrogen is the other one, but hydrogen's kind of a weirdo. We'll talk more about it later. The non-metals are over here. And we typically do include hydrogen as a non-metal, which is why it shows up twice. Again, when we talk about the periodic table, we'll talk about why it shows up twice. It's treated as a non-metal. It behaves as a non-metal. There are what are called, I know Mr. Voorhees calls them the heavenly seven. You may have heard that in physical science. They're the 7 elements that are diatomics. So they always appear sort of holding one another's hand. Oxygen, nitrogen, oxygen, hydrogen, fluorine, chlorine, bromine, iodine. 1, 2, 3, 4, 5, 6, 7. That's it. So it forms this sort of little weird shape. But those are the nonmetals. Pretty important to us as carbon-based life forms. Pretty handy. Oops, wasn't recording. Okay, neither fish nor fowl. Some characteristics of each. Tend to conduct under only certain conditions, and silicone is the best known, the one that we use the most at present. If we look at where these things lie on the periodic table, and I'll do these in green. So silicone, germanium, arsenic, tellurium, acetane. No, acetane is a noble gas. I always have to cheat to get these right. No. Yeah, really. I do. There's germanium, selenium, and possibly something like that. Boron. I have to cheat. But they're in this little wiggly line over here. I think germanium, now that I think about it, is actually a metal. Yeah. There. That looks better. And actually I think polonium is considered a metal. There aren't a whole lot of them. They're a little teeny tiny, and if you look in your book, we'll look at the periodic table. I'm not holding you responsible for which is what yet. Like I said, silicone is the best known of them, and there's not a whole lot more to say about them. The fact that they are semiconductors is kind of the most critical piece in terms of what we need to know about them for now. Though they do not typically, the noble gases are generally unreactive. There have been 2 compounds that I know of that have been found to form with noble gases. It's a weird thing, and it's been pretty recent that we've realized that can happen. As their name implies, they are gases at room temperature. A lot of these are used in lighting. Neon lighting is actually a tube full of low-pressure neon that you run an electrical current through. You have a gas at low pressure. You run an electrical current through it. Guess what it does? It glows. It becomes a plasma. Yeah, because you're adding energy to the electrons in the neon. Argon, krypton, and xenon are also used in the same way. Argon is also used in welding. Does anybody know how? Anybody ever done any welding? Okay. Anybody ever seen rust? Okay, what is rust? It's oxidation of a metal. Rust specifically, we typically are referring to iron. Iron will oxidize in contact with air. with the oxygen in the atmosphere. The hotter it is, the more likely it is to react. You heat it up, it's going to react more quickly. So if you've got a nice, beautiful, gleaming welding seam sitting there in all that lovely oxygen, what's very likely to happen to your beautiful, shiny, new seam? By the time it cools off, it may be rusted. So what's done is something called gas-shielded welding, and you have your beautiful red-hot bead, and at the tip of the little welding gun there is a stream, I'll color it black, there's a stream of argon. Argon is non-reactive. Argon pushes the oxygen out of the way and cools the metal simultaneously so that you don't get immediate corrosion on that beautiful gleaming little seam. It's pretty handy. And argon's one of the many things that they pump. I think it might actually be the primary thing. Where do you get argon? It's just in the atmosphere. All these things are just in the atmosphere. And if you condense enough atmosphere, if you pull atmosphere in and you condense it down to the point where it's very cold, you can separate them easily. And the Lind plant down on the river, it's down by Mountaineer, they actually pump argon out of the atmosphere. It's there for free. They're mining the atmosphere for argon, basically. So, okay, that is it for Chapter 1. It is a brief introduction. You're going to have some time today to work on questions, to work on labs. While you're doing that, I'll be frantically working to get your lab A1 packets back. I'd rather chew my own feet off. I hate that lab, but it's a good lab because it gets you exposed to a lot of different pieces of equipment. Questions, comments, concerns? You got time to work?